The last, not really theorem, I'm calling it a theorem, but it's really not. It's Descartes' rule of signs. The guy is named Descartes. This is his rule of signs. So it's Descartes' rule of signs. It turns out that if you have some sort of polynomial like this, I don't know how long this polynomial is. It doesn't matter. That's what this dot, dot, dot in here means. I have all these terms. It could be 150 terms. It could be 3 terms. Doesn't matter. Okay? Don't get confused by the notation. Descartes' rule of signs is this. The number of positive real zeros for the polynomial is the same as the number of sign changes in the coefficients of the terms, or is less than that by an even number. So what you're going to do is you're going to count up the number of times the signs change. That number is the highest number of positive real zeros in that polynomial. Or you could have 2 less than that, or 2 less than that, or 2 less than that, all the way down until you don't have any numbers left. You'll see what I mean in a minute. The number of negative real zeros of the polynomial. So these are negative real zeros. So if you were to solve, you would find x equals like -2 or something like that. Okay? The number of negative real zeros is the same as the number of sign changes, again, in the coefficients of the terms of the polynomial evaluated at -x. Or, again, less than that by an even number. So for the number of positive real zeros, you're just looking at the original polynomial straight up. For the number of negative real zeros, you are substituting in -x and evaluating that down. And once you've done that, count up the number of sign changes. And then you'll have the number of possible negative real zeros. These are just possible zeros, again, not guaranteed zeros. So keep that in mind. Just like with the rational root theorem, we were only finding possible rational roots. So let's practice on this one. State the possible number of positive zeros, negative zeros, and imaginary zeros of the polynomial. Well, in this polynomial, how many zeros am I going to have total? Yeah, because it's a 6th degree polynomial, so there's going to be 6 zeros. So the way that we're going to solve these types of problems is we're going to set up a table. The table is going to say number of positive zeros, number of negative zeros, number of imaginary zeros, and then the number of zeros total. If I add up the number of positive zeros, the number of negative zeros, and the number of imaginary zeros, I should get the total number of zeros that I'm supposed to have for this polynomial, which is, in this case, 6. There's your table. We know we're supposed to have 6 total zeros. I'm going to put a 6 there. Now, using Descartes' rule of signs, we look at the polynomial and we count up the number of sign changes that we see. So let me clear off. I drew my little lines a little bit too high there. Okay, now we can actually see it. How many sign changes do I have? Well, I start off positive. Okay, so then I go to the next term and I'm still positive, so I don't have any sign changes yet. But then I switch to negative. That's 1 sign change. I stay negative. That's not a sign change. I switch to positive. That's another sign change. I switch to negative. That's another sign change. And then I switch back to positive. That's another sign change. So how many sign changes did I have? 4. Now I need to find the possible number of negative sign changes. In order to do that, I have to find f of negative x, which means I'm substituting in negative x everywhere that I see x. Use parentheses. F of negative x equals, parentheses, negative x to the 6th plus 3 times negative x to the 5th minus 4 times negative x to the 4th minus 6 times negative x to the 3rd plus negative x squared minus 8 times negative x plus 5. Now the question is, how do I simplify this down? I have to simplify this before I count up the number of sign changes here. The way that you do that is, think about, what is negative something to the 6th power? Do you get a negative result or a positive result? Like if I take negative 2 and I square it, what do I get? Positive 4. If I take negative 2 and I raise it to the 4th power, what do I get? Is it positive or negative? It's positive. If I take a negative number and I raise it to the 6th power, am I going to wind up with a positive result or a negative result? Positive. Because when I raise something to an even power, it will always be positive. So this negative x to the 6th power turns into just x to the 6th. So now I have f of negative x equals x to the 6th. Now what happens if I raise a negative number to an odd power? It stays negative, that's right. Like negative 1 to the 1st power is still negative 1. Negative 1 to the 3rd power is negative 1 times negative 1 times negative 1, which is still negative 1. Negative 1 to the 5th power, same idea. So if I'm raising something to an odd power, this sign change will actually occur. It will stay negative. So now what I have here is 3 times negative x to the 5th, which is negative 3x to the 5th. So I'm going to write minus 3x to the 5th. That odd exponent caused my sign to flip here. On this one, will this exponent cause my sign to change? No. It will stay x to the 4th here. So I still have the negative 4, the minus 4, x to the 4th. So minus 4, x to the 4th. Will my exponent here cause my sign to change? Yes. The odd exponent makes the sign change. So instead of minus 6x to the 3rd, it becomes plus 6x to the 3rd. Will my exponent cause my sign to change here? No. So it's going to stay plus x squared. Will my exponent cause my sign to change on this one? Yes. So instead of minus 8x, it becomes plus 8x. And I didn't do anything to that plus 5, so it stays plus 5. So let me go back over that again, because I want to make that connection really hit home. If I'm plugging negative x into a polynomial, and I'm raising a negative something to an even power, what happens to the sign? It stays the same. If I raise a negative number to an odd power, what will happen to the sign of my term that I'm dealing with here? It'll change. Okay? Because if I raise a negative number to an odd power, this negative sticks around. And then the negative times the sign out front will change that sign. So if I have an odd power, you probably want to write this down somewhere. I don't have it in the notes, but you want to write it down. If I have an even power, when I find the negative real zeros, and I substitute in negative x, an even power, the sign is going to stay the same. An odd power, and the sign is going to flip. So we started with positive x to the 6th here. It stayed positive x to the 6th. With the odd power, the sign flipped to negative 3x to the 5th. With the even power, the sign is going to stay the same. With the odd power, the sign is going to flip to positive 6x to the 3rd. With the even power, the sign is going to stay the same. So it stays positive x squared. With the odd power, the sign is going to flip. So plus 8x. And then the plus 5. Now we count up the number of sign changes in this polynomial, and that will give us the number of negative possible real roots. So we start off positive, we switch to negative. That's one sign change. We stay negative, no, we switch to positive, so that's 2 sign changes. Then positive, positive, positive. How many sign changes do we have? 2. My total should be 6. Is my total 6? Yes. So how many imaginary roots would I have in this case? 0. So now the thing of it is, this says the number of positive real zeros is the same as the number of sign changes in the coefficients of the terms, or is less than this by an even number. So that means I can have 4 positive real roots, or I can have 2 positive real roots. And then I can still have that 2 negative real roots. I need 6 total roots, which would give me how many imaginary roots here? 2. Or I can go less than this by 2 also. I can have 0 positive real roots. I can still have the 2 negative real roots. I still need 6 total roots, so in this case, how many imaginaries would I have? 4. Or I could have kept the 4 the same here. I could have 4 positive roots and 0 negative roots, because I can decrease 0 by 2 as well, or is less than this by an even number. So that would be 4 positives, 0 negatives, 2 imaginaries for a total of 6. And once I've gotten rid of this one, I can continue to decrease this one back to 2, 0. And how many imaginaries in this case? 4 for a total of 6. And because that's still higher than, or 2 or higher, I can go down even more. 0 positive, 0 negative, every root imaginary for a total of 6.
Okay, do we have to do that?
Yes. Descartes' rule of signs is this entire table right here.
So you can't go above.
You cannot go higher than the number you wrote here. You cannot go higher than the number you wrote here. You cannot go higher than the total number of zeros that you're supposed to have. But you can decrease this number by 2 until you get down to either 1 or 0. It's always decreasing by 2, never 1. Okay? So in a little bit, we're going to do an example where we have like 3 possible positive roots. Since that is higher than 2 or higher, we can decrease that 3 down to 1. But we can't decrease the 1 down any farther than that, because I can't subtract 2 from 1 and get 0. I get negative 1, which isn't possible. Okay? So it's only if you have 2 or 3 or 4 or something like that. So you can decrease, and you have to come up with all the possible combinations. So what I do is I hold the negatives constant. I decrease all the positives until I'm down as far as I can go, rewriting that negative 1 each time, that negative column. Then I decrease the negative column and start over. Then continue. And you might have to continue and decrease again the negative column and continue. You'll see. But this is the idea. So now the nice thing about this is, the nice thing about Descartes' rule of signs is, I know that if I find a positive real root, I know that there's another one. Because if I find one, I'm guaranteed 2. If I find a negative real root, I'm guaranteed to find another one. Because if I find 1, then there's definitely 2. Okay? That's what Descartes' rule of signs does for us. Now there's going to be polynomials that I can give you where, based on what happens, you might not have any possible negative roots. And when you combine that with the rational root theorem, all the plus and minuses that we have, if I can't possibly have any negative real roots based on Descartes' rule of signs, then I don't need to check those numbers, which means I can narrow down my search for those real roots. So this is a very nice tool to have, and that's why we're learning it. All right, state the possible number of positive zeros, negative zeros, and imaginary zeros of this polynomial. So it says state the possible number of. That means I'm going to just draw my chart. So I have number of positive, number of negative, number of imaginary, and the number total. How many total am I supposed to have? 5. Okay, so count the number of sign changes in the polynomial that you see, and that will be the positive possible roots. So, how many sign changes do we have? We start positive, stay positive, switch to negative, that's 1. Stay negative, switch to positive, that's 2. So we have 2 possible positive real roots. Now we need to find h of negative x, so that we can find our possible negative roots. Yeah, you should write it down, because otherwise you might get confused. It's not that hard to do. We saw the pattern. We know how these signs are going to change. Will my sign change for 2x to the 5th? That is an odd exponent, so yes, my sign is going to change. Negative 2x to the 5th Will my sign change for x to the fourth? No, so it stays plus x to the fourth. Will my sign change for 3x to the third? Yes, so minus 3x to the third. Will my sign change for the next one? As an even exponent, the sign does not change there, so minus 4x squared. Will my sign change for minus x? Yes, that's an odd exponent, so it turns to plus x, and then the plus 9 doesn't change. Now count up the number of sign changes here. How many do we have? We start negative. We switch to positive. That's 1. We switch to negative. That's 2. We stay negative. We switch to positive. That's 3. We stay positive. There's 3 possible negative real roots. How many do I have written down? 5. So how many imaginaries would I have in this case? 0. Okay, now we apply the rest of Descartes' rule of signs. Hold the negative possible roots constant and decrease the positives if you can. Can we decrease the number of possible positive roots? Yes, to 0. I've held the negatives constant, which means I need how many imaginaries to balance this out? 2 imaginaries for a total of 5. Can I decrease the number of positive roots any farther? No. It's already at 0. 0 or 1, and that's it. Okay, so I can't decrease this anymore, which means I'm going to reset what I had back to 2 and decrease the negatives. Can I decrease the negatives? Yes, down to 1, which would give me how many imaginaries? 2 for a total of 5. Okay, hold the negatives constant. Can I decrease the positives any? Yes, I can send the positives to 0. I can have 1 negative still. How many imaginaries would I have here? 4 for a total of 5. Okay, that's as far as I can go with the positives. Can I decrease the negatives anymore? No. Once you're at 1, you can't go any farther. So this is the table. The answer, state the possible number of positive, negative, and imaginary zeros. This table is the answer. We can have 2 positives and 3 negatives. We can have 0 positives, 3 negatives, and 2 imaginaries. We can have 2 positives, 1 negative, and 2 imaginaries. Or we can have 0 positives, 1 negative, and 4 imaginary zeros in this particular polynomial. I don't know exactly what it is, but I do know that these are the only possible combinations of zeros in this polynomial. Now the nice thing is, if you look at the negative column, I'm guaranteed 1, 0 in this column. So if I combine this with the rational root theorem, I'm only going to check the negatives because I'll find this one for sure. And that will get me down to a 4th degree polynomial. And then I could work from there. Okay? So that's the idea. That's where we're headed. In fact, we're headed there now. The directions switch. From state all the possible number of positive, negative, imaginary zeros, we switch to find all the zeros. In order to do this, we're going to apply Descartes' rule of signs and the rational root theorem together on this problem to help us narrow down the search. Because I have this 80 sitting right here, and there's a lot of factors in 80. Okay? I'm trying to narrow the search down as much as I possibly can. P's and Q's and P over Q. Start with P. Why? Like we just did? Oh, we're going to anyway. Start with P. What are the factors of... For P, we go to the constant term, which is 80. I need the factors of 80. Okay. Does 3 go into 80? 4 does. 5 definitely does. How about 6? You sure? Why? 3 doesn't.
2 and 3 have to go into.
Yeah, so 3 doesn't go into it, which means 6 doesn't. How about 7? 8? 9? 10. Okay, 10 times what is 80? 8. And we already have that one. So now we can just work backwards and get the other numbers. So 5 times what is 80? So plus or minus 16. Then what? There's all your factors. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20 factors that we would have to check. Okay? Now let's use Descartes' rule of signs. Hopefully we can narrow this search down. So, oh wait, no, I'm sorry, we didn't do Q's yet. Q equals what? Plus or minus 1. So then P over Q equals that. So I just got a little bit ahead of myself. It doesn't change the number of possibilities. Okay, now Descartes' rule of signs. So number of positive possible roots, number of possible negative roots, number of possible imaginary roots, number total. Number of possible positive real roots. How many more adjectives can I use on roots? How many sign changes do we have in the positive polynomial? Start positive, switch to negative, switch to positive, so 2. We can only have 4 roots total. So? That's okay. Nope. Missing terms don't matter here. Missing terms matter when you set up your synthetic division. Okay, so now we need to rewrite our polynomial with the negative x. So f of negative x equals what? So it's x to the 4th. Is it plus? It stays minus. This is an even degree here, so minus 18x squared. This one does change, minus 12x plus 80. Okay, how many sign changes here? 2. So if I have 2 positive and 2 negative roots, how many imaginaries would I have? 0. Okay, now set up the rest of the table. So, hold the negatives constant. Can we decrease the positives? To what? 0. 2, which means I need 2 imaginaries for a total of 4. Can I go any lower on those positives? No. So reset it. Can I go lower on the negatives? All right. So I have 2 possible positives, 0 negatives now. 2 imaginary, 4. So hold the negatives constant. Can I decrease the positives here? Yes. To 0. 0. 4 for a total of 4. I've taken care of all the possible combinations now in this table, which means that now I have all the possible positive and negative and imaginary combinations for this polynomial. I can have 2 positives, 2 negatives, 0 imaginary. 0 positive, 2 negatives, 2 imaginary. 2 positives, 0 negatives, 2 imaginary. Or all 4 of them imaginary for this polynomial. So what that means is, if I find one that's positive, I will be able to find another that's positive. If I find one that's negative, I will be able to find another that's negative, guaranteed. Okay? I don't have a nice situation like this where I'm guaranteed to find a negative one, but I do know that if I find one, I'll find another. How many do I need to find before I can stop and use the quadratic formula? I need to find 2. I need to get this down to a 2nd degree polynomial. So I have to find 2. It doesn't matter if I find 2 positives or 2 negatives, but I got to find 2. So now we set up our synthetic division. And as was mentioned, we need to include all of our missing terms as well. So what will go across the top? 1, 0, negative 18, 12, 80. Now I'm going to start choosing numbers. Do you want to try to find a positive real root or a negative real root? Negative? Okay, there may be something to that. Noticing that we only have one negative sign here, maybe the negative sign needs to be over here so that we wind up keeping our numbers down to where we get a negative answer here, okay? That's a great thought. So if you want to try negatives, let's try negatives. Where do we start? Okay, negative 1. The 1 comes down, times negative 1 is negative 1, plus 0 is negative 1. Multiply and I get 1. Add and I get negative 17. Multiply and I get 17 plus 12 is 29. Is this one going to work? No. So as soon as you see it's not going to work, you can stop. You're not going to finish it. Well, negative 1 didn't work, but that doesn't mean we're doing things wrong. Try another one. You want to go to negative 4? Why? Okay. Yeah. It's just a guess, really. So negative 4, let's try that one. Maybe it'll work. 1 comes down. Negative 4. So that's 16 plus negative 18 is negative 2. So that's 8 plus 12 is, yeah, hopefully it's still 20. And then times negative 4 is, negative 80 plus 80 is 0. You found one that works. Nice job. Now, because I found this one, I'm guaranteed to find another one of the same sign because of what I have sitting over here in this table. So that means that we're sitting on either this one right here, this situation, or we're sitting on this situation. But guaranteed, we're going to find another one. Okay? So now I'm going to use this same polynomial right here. I'm going to draw my line. This is my new polynomial, and I'm going to continue. I already know that negative 1 doesn't work. And then, once we find another one, then we'll be down to a second degree polynomial, and we can use the quadratic formula or the box method to get the other two answers. Okay? So here's the thing. I already know negative 1 doesn't work. I know negative 4 works, but negative 4 could work again. We could have a double root. So you would want to check negative 4 again just to make sure that you don't have a double root situation. Sometimes people will forget that that's the case. So the 1 comes down. Negative 4 plus negative 4 is negative 8. So positive 32. So that's positive 30. Is this one going to work? No. Okay, so negative 4 didn't work. It's worth it to check, though. Okay, you want to try negative 2. That's fine. The 1 comes down. Remember, we're on this line right here. The 1 comes down. 1 times negative 2 is negative 2. So we get negative 6. Times negative 2 is 12. Plus negative 2 is 10. 10 times negative 2 is negative 20 plus 20 is 0. This one works also. You're guessing pretty good today. So negative 2 worked. We found our two negative real roots. So now we're down to x squared minus 6x plus 10 equals 0. We're down to our second degree polynomial, which means we can use either factoring or the box method or the quadratic formula. Does it factor? There's no a here. The a is 1, so I don't need the box. I just need two numbers that multiply to give me positive 10 and add to give me negative 6. Do we have two numbers that do that? 2 times 4 is 8. Do we have two numbers that do that? No. So this does not factor, which means I need the quadratic formula. No, I did not say that. No, I did not say that. X equals negative 6 plus or minus the square root of 36 minus 4 times 1 times 10, all divided by 2. So x equals 6 plus or minus the square root of 36 minus 40. Negative 4. Divided by 2, which simplifies. X equals 6 plus or minus what? Well, the square root of 4 is 2, so it's 2i over 2. Does that reduce? Yes. X equals 3. Two complex roots, two imaginary roots. and 2 negative roots. So that means that we were on this case right here, 2 negative roots and 2 imaginary roots. So notice now that using Descartes' rule of signs and using the rational root theorem lets us narrow down our search, and because of this table, we knew that we could find another one to get us down to that second degree polynomial. So believe it or not, this work that you're doing on this problem actually makes your life simpler. We have x equals -4, x equals -2, and x equals 3 plus or minus I. Those are the 4 solutions. Those are the 4 roots. So the directions say find all the zeros of this polynomial. Where should we start? P. The factors of the constant term. P equals? Yep. 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 Not 4 or 5? Okay. Yep. Okay. How about Q? Look at how kind I was giving you a leading coefficient of 1. You're welcome. Q is the factors of the leading coefficient, which in this case is 1. So on the last one, the same thing was true. But if there was a 2 here, we'd have plus or minus 1, plus or minus 2. Okay? P is the factors of the constant term. Yeah, 18. All right, so P over Q. Those top numbers. Yeah, convenient. Okay, what happens now? Make your Descartes' rule of signs. So number of positive, number of negative, number of imaginary, number total. I have no idea how I write so fast. It's probably because my handwriting is terrible. How do we find the number of possible positive real roots? Sign changes in the original polynomials. There are no sign changes in the original polynomial. So how many possible positive real roots do we have? 0.
There's 0 negatives.
How do you know that? You don't know that. Change the f of x to f of negative x and change the signs for the ones that need to be changed. X to the third changes. Negative x to the third. 2x squared stays the same. Plus 2x squared. 9x changes to negative 9x. 18 stays the same, positive 18. How many sign changes do we have? We start negative, change to positive, change to negative, change to positive. We have 3. How many total real roots should we have? 3. So how many imaginaries would I have here? 0. Now what do we do? Decrease if we can. Can I decrease this one? No. Can I decrease this one? Yes. So this will still be 0. This will be 1. This will be, and this is, okay. Can I decrease this? No. Once I have a 1 here, I can't go any farther than that. So this is it. You can never increase from the number that you wrote down here. Descartes' rule of signs in the definition specifically says, once we get this number, we can decrease that number by 2 to get another row. And we can keep doing that until we are at either 1 or 0, and then we can't decrease any farther. One thing I will say about the imaginary roots is you're always going to have an even number. It's either going to be 0 or 2 or 4. It's never going to be just 1 or 3. Partly because of the conjugate root theorem. If a plus bi is a root, then a minus bi is also a root. So imaginary roots occur in pairs. And that also comes from when I decrease this by 2, I have to keep that balance of 3 so that 2 goes there. Okay? Now, this is it. This is as far as I can go. So I actually didn't need these long lines in this table. I only have 2 possible scenarios. I have 1 real negative root, or I have 3 real negative roots. This polynomial is what degree? Third degree polynomial. So I only have to find 1, which means that all these numbers that I have to pick from, I'm only going to check the negatives because I don't have any possible positive roots. I have only possible negative real roots, and I'm guaranteed to find one. So I'm going to find that one. Set up your synthetic division.
-2.
1, 2, 9, 18. We're only checking negatives. What do you want to start with? -2? Did you try it already and you know that it works? Okay. -2. The 1 comes down. -2 plus 2 is 0. One comes down. 1 times -2 is -2. Plus 2 is 0. 0 times -2 is 0. Plus 9 is 9. 9 times -2 is -18 plus 18 is? So -2 did work. -2 is one of the roots. Now, does that mean that I can't find the other two negative ones? It does not mean that. I could continue if I wanted to. Do I want to? No, I don't want to because I'm down to a second degree polynomial. So my polynomial now is x squared plus 9 equals 0.
Wait, so couldn't we do two things to add to get to 0?
You could factor this right now.
X minus 3.
Or you can see that you only have two terms sitting here, only one x term. I'm just solving for x. How about I use the square root property? Subtract 9 from both sides, and I have x squared equals -9. So I square root both sides, and I get x equals,
X equals 3.
thank you, plus or minus 3i. I found all three of them. X equals -2. X equals plus or minus 3i. This last problem we've already kind of seen before. It's worth bringing back up though. It says the volume of a box is that. The length is 1 centimeter more than the width and the height is 3 centimeters less than the width. Find the dimensions of the box. What do we do? Okay, label the sides. Length, width, and height. We need to define a variable. How about x? What is x? It's the width. Why are we picking the width for our variable? It's comparing it to both of the other two sides. So x equals the width. Now that I know the width, what's the length? So if the width is x, then the length is x plus 1. And the height is x minus 3. And it gives me the volume, which means I need to do what with my dimensions?
Add them all together, or multiply them all together?
Multiply them all together. And if I multiply them all together, I get 1056. So my equation is x times x plus 1 times x minus 3 equals 1056. Now what? The original point of this problem was for you to FOIL this out and distribute the x in and move the 1056 over and then use Descartes' rule of signs and the rational root theorem to come up with all the possibilities and then use all of that to come up with your answer. My solution is to graph it. Remember to include parentheses in between. And I need to move that 1056 over. So I close my parentheses and then I subtract 1056. Press enter and I don't see anything. That's because my solution is sort of off my graph. I need to zoom out some and there we go. Then just like we did in the previous section, analyze graph, find the 0. When I find the 0, what dimension did I just find? I found the width. So now I know that the width equals 11 centimeters. And the length equals 12 centimeters. And the height equals 8 centimeters. So the point of the problem in this section was to use Descartes' rule of signs and the rational root theorem after you got to this equation right here. But if we're looking for roots, why not use the calculator and have it find it?
Wait, where did I go wrong?
So that's it for the section. The last three problems are now yours.